Here we are, it's the Physics 2A video lecture. Physics 2A video lecture 5. And I'm going to begin with some announcements about note-taking and other things like that. So, first of all, we're emailing the notes in, and we're going to email twice, notes and homework. So email on Friday by 6 o'clock p.m. First one is your name, Physics 2A notes. So that's your subject line. And the second one is your name, Physics 2A homework. So yeah, we want to send them in separate emails. And the notes are just for the Monday, Wednesday, and Friday lectures of each week, or whatever we had going on that week. So for example, the next ones will be lectures 3, 4, and 5. This one. Okay, they'll be turned in Friday, 6 o'clock p.m. The homework will always be everything 3 lectures before that. So it'll be last Friday, Monday, Wednesday. Okay, and then you'll turn that in. On the Friday. So today's lecture, video lecture 5, you would turn the homework next week so you had enough time to look at it. Okay. So that should be simple enough. And it's very important to take notes every time and not put it off. So because of that, in order to help you with that, I'm going to be posting one lecture at a time. So starting next week, there will only be one lecture up at a time. So for example, when video lecture 6 goes up onto the YouTube channel, 1 through 5 will no longer be available. And then when 7 goes up, 6 will no longer be available. And yeah, I'll keep the lectures up at, a day or 2 for sure, so you have a chance to look at them more than once if you want to. Okay. The construction of your notes is a very important part of the semester, especially because of our current circumstances. So that's why I recommend you being very thorough and neat and leaving a lot of space. You can come back to the notes and improve on them, make corrections, and so forth. Good, so that's what we're going to do. 2 emails, each one with your name, Physics 2A, and then one of them is the notes and one of them is the homework. Good. I think that about covers it. Oh yeah, there was one more issue. So since I just mentioned that, I'll write it down here. One video in the YouTube playlist. So only one at a time. Maybe when exams come up or final exam or what have you, can do reviews and put more back up, but they're just going to be one at a time. One at a time. And homework solutions. Now that we have a week behind us, I'm going to start doing homework solutions. So after you've turned things in, the following lectures, I'll devote the beginning of each lecture to solving a problem. You guys may have some that you're interested in. You can email me about that. Otherwise, I'll just choose what I think is most important for you. So homework solutions will be during lectures. And that's an important part of the feedback. I'm not grading your homework. I'm just checking that you did it. And I hope you did a neat job for full credit. Same with the notes. So the feedback you're getting on the homework is when I do these solutions right here at the whiteboard, and then you can make comparisons and correct your work. Good, so that is all of our announcements for the day, and now we can get back to doing physics. Here's an older lecture. So we ended having discovered the laws of constant acceleration motion. I'm going to write those formulas down, discuss again what they mean, do some graphing, and then we'll apply them to free fall. And I'll even warn you, these next two chapters, the rest of chapter 2 and 3, they a lot of formulas, but we're just going to work our way through it. It gets easier with practice. So what we're talking about is motion with constant acceleration. And these are the kinematic formulas. After you write them down often enough, they'll just, you don't have to try to memorize them. You write them down often enough, it'll work. So constant acceleration kinematics, we have position equals initial position plus velocity times time plus 1/2 acceleration t squared. Velocity equals v0 plus a times t. And then this third equation that I derived is very useful. What we do there is we eliminated the time and we're just relating the speed squared, the acceleration, and the distance, okay, and the position. So those are the formulas that we can do everything we have to do with, basically. Okay, so we started out though with free fall, and I'm also going to put the free fall equations up right next to these. So in the case of free fall, and that is no more and no less than the ball dropping out of the sky, okay? When it's falling, it's in free fall. Okay, that's the motion we're talking about. So for free fall, the acceleration, 8 meters per second squared. So this g itself, notice minus and minus, the g itself is a positive number, always, okay? Because I have minus here and minus there. G is a positive number. I put the minus sign in by hand, and I have x equals x0 minus 1/2 gt squared, b equals b0 minus gt equals b0 squared minus 2g x minus x0. And for the free fall, our x-axis is the positive vertical axis. Okay, we're calling x the positive vertical axis. And if we were going to graph this thing, we would have t right down here. So maybe the first thing we should do is just talk about this formally and ask, what does the graph look like? Okay, because constructing graphs is a great skill, and it's position versus time. When time is equal to 0, we have 0 to 0, and x is equal to x0. So that's an intercept. That's an initial position. Now, if we start off the ground, or if we declare the tabletop to be 0, then this could be 0, and we could launch up and down as well. Okay. But just for the sake of completeness, this is the initial position, and this would be the 0 level. You got 0 there and there. And then what? Well, suppose there were no gravity. If there were no gravity, this would just be the equation of a straight line. So I'm going to do a dotted line with a positive slope. Okay. That's what this function would be without gravity. Should we get the 2 there, okay? That's a 2. but there is gravity. You know, you can imagine if there were no gravity and I throw this ball, it would just drift up out of sight, okay? There is gravity, so it's gonna fall back down, and that's this quadratic part, -1/2 gt squared. The quadratic part wins out over the linear part here as t grows, and so we get something like that. So if I threw the ball up in the air, it would go up, it would reach a maximum height, then it would fall down and go down to my feet, okay, and it would land on the ground, and there would be a certain time involved for that all to happen. Okay, so what we're going to do is just this same analysis with a simplified version, and we'll try to answer every question we can about throwing something in the air, having it come back down to us and catching it. That's the goal. See if I can do that, right? Throw it up in the air, and then I catch it. That's free fall. And what we can agree on for simplicity is that the level at which it reaches, it leaves my hand, that's the 0. Okay, that's where I start measuring. And then I'm going to catch it at the same level that I released it from, and it came back to 0 again. Okay, so throw it up in the air, catch it, and then it will be this graph in a simpler form. So that's what I'm going to do next. And you know, for the rest of the hour, we should probably just work on this board and leave these formulas up there. Just keep referring back to them. So here's our example. Vertical, we'll call it a vertical launch. Vertical throw, vertical launch, so we'll call it a vertical throw. That's what we're talking about. We have x of t. Title of this thing is vertical throw. I just demonstrated it for you. But we're saying we're going to launch it from here, and it's going to go up in the air, come down. Remember, this is the t-axis. You can say the clock is ticking while the ball is coming up in the air, coming back down again. So what happens is, at some time here, it reached its maximum. So that's x maximum, that's the maximum height. And then when it hits the ground again, let's go ahead and call that the air time, just to give it a name. That's the time it was in the air. Okay, so this is on the graph. In reality, it just went straight up and came down to my hand. On the x versus t graph, it went up and came down, and all the while the clock was ticking in so and so many seconds. We'll prove in a little bit that it reaches the top at exactly half the time that it takes to go up and come down. But now let's do the analysis. We're using that formula up there with x equals v0t minus 1/2 gt squared, because we're starting down at the origin, okay? So here are the questions we're going to answer. Questions: how high? In fact, we'll actually do them in different order. Air time equals question mark, and the other one is how high does it go? We can answer any question about this thing. We'll start with these two. So to get the air time, there's a really easy way to deal with this, and that is to factor out 1 power of t. So t times v0 minus g times t over 2. Okay, so this is equivalent. I factored out time. Therefore, you can see that x equals 0 when the time equals 0, and x equals 0 when the time equals air time. And to find that, we set this expression in parentheses equal to 0. So V0 minus GT air divided by 2 is equal to 0. We set this parentheses expression equal to 0, solve for T air. T sub air is equal to 2V0 divided by G. Now you'll notice I'm not plugging any numbers in. Beginning students would love for me to plug numbers in, but it's not necessary most of the time, okay? For a particular problem, we would plug numbers in, but you would want to get the answer first and then put some numbers in. So this answer is very interesting. You can do, first of all, the dimensional analysis on it to make sure that you're going to have seconds here and seconds over here, and that in fact is the case. Do that if you want to. Leave some room in your notes and do the dimensional analysis here. It'd be very good. The second thing is to see if this makes any sense. And that's why a formula is good. Suppose I throw it faster. Okay. Suppose you throw it faster. I throw the ball as hard as I can. You got a better arm, you throw it twice as fast. Okay. Well, if V is greater, then the air time is greater as well, which is a reasonable result. Okay. Because you throw it faster, it goes higher, takes longer to come back to your hand. And we could even say something about G here, because if you did this experiment on the moon, G on the moon is much less than G on Earth, 1/6 the magnitude. And then you throw something in the air, or the lack of air, but you throw it up, and it takes 6 times as long to come back to your hand. Okay, that would be interesting. So yeah, there's a lot of physics here if we learn how to evaluate and discuss these formulas. And now's the time to start learning. So we found the air time. Plug your initial speed in, you find out how much time it spent in the air. Now, how high did it go? Now, there are 2 ways to get the height. I could plug in half the air time into this formula, or I can use this third, oh, not that one. I can use this third formula here. And I'm going to use this third formula just to demonstrate its use. Answers, of course, will be the same. Doesn't matter what formula you use. Answer will be the same. So to find out how high, so this question, we're going to use V squared minus 2G x minus x0. And here's the thing. When we reach x max, V0, V is equal to 0. So we're going to evaluate this formula as follows. 0 equals V0 squared minus 2G parentheses x max. But what was x sub 0? X sub 0 was 0. Okay. So using different color, right, we struck that equals 0. This was x max, and this was 0 at the top when it came to a stop. Okay. And so now, got room right here, I'll put this right here. So we're going to solve for x max. So the maximum height is equal to V0 squared divided by 2G. Hope that shows up on the tape. V0 squared divided by 2G. Let's see if I can clean that up a tad bit. 2G, yeah. So we answered those 2 questions. And really everything can be answered with these three formulas. So I'll go ahead and erase this. I'm going to leave those formulas up, and we will keep answering the question. In fact, yeah, I'll erase them all, but we're going to keep talking about the vertical throw. I'll repeat this graph and then I'll add something to it. Okay. And oh, by the way, you could do your dimensional analysis here too. Leave some space in your notes. Make sure that you get meters on both sides. That's very good practice. Also, in terms of, there's so much physics here. This is a really interesting one. The maximum height is proportional to the initial speed squared. Okay. What that means is if I can throw it twice as fast, it will go 4 times as high. Okay. If I double a speed, 2 squared is 4, I'll get 4 times the height. So think about that too. These relations will be repeated throughout the semester. Okay, I will erase and do the same example with a slight twist. So we're still doing the vertical throw. I want to illustrate something that I just mentioned. So vertical throw once again. And this time what I'm going to do is do 2 graphs, so I have to leave enough room. So this is t and x, position versus time, x versus t is the graph. And we just saw that we get something like that. Qualitatively the same thing. And that was this first function. Now let's go ahead and have a look at this second one here. And I'm going to use the same time scale, but notice how I do this. There's a lab that we always used to do this graphing business, so we'll see. Important. So I have the same time scale. I have V, and this now is in meters per second. T is in seconds. Go ahead and meters. There we go. Same time scale, but a different vertical scale here. Now this is the velocity. And the function here is V equals V0 minus GT. But what does this thing look like if you graph it? Okay, so I'll just have a V versus T, V versus T. All right. What does this look like? It looks like a straight line with an intercept and a negative slope. So a straight line with an intercept at V0 and a negative slope. And since it's a straight line, it goes like this. And what you'll find is at the end of T air here, the value has gone over to minus V0, and it crosses through the 0 at exactly 1/2 of T sub air. Okay. V equals 0 when T equals, I'm just solving, plug in a 0 and solve for T, V0 over G. Okay, so that's half of T air equals 1/2 of T air, which you have in your previous notes. So that's really interesting. So what is this V equals 0? That's right there. It starts out positive. Here's a slow motion. So it leaves my hand, it goes up, stop, once more. Okay, it leaves my hand, it's rising, comes to a stop. Okay. Rising, comes to a stop, turns around, comes back down. When it hits my hand, it has the same speed with the opposite direction that it had when I released it. Okay, so that is now a pretty thorough discussion of the vertical throw. knowing these things, you realize at any time between 0 and t air, you can know exactly where the ball is, what its height is, and you can know exactly how fast it's going. So any time as the clock is ticking between when it leaves your hand and when it comes back. Okay, I'm going to consult with the clock here. Okay, excellent. So we have time for plenty of other examples. And yeah, this is an important chapter. But the vertical throw is the thing to start with. Now I'm going to do a little more free fall. A little bit more free fall. Let's see. Let's just call this more free fall. Let's release. Okay. We're going to release an object from a certain height. Release an object from x equals h, or I could even say from x0 equals h. And if I release it, I mean I'm just dropping it, I'm not throwing it. So the graph, the function for that would be x is equal to h minus 1/2 gt squared. See, I've changed the name of x sub 0 to h because it's the idea I'm releasing it from a height. And it's not getting any initial speed, either up nor down, so that term is gone, and it's just h minus 1/2 gt squared. And I'll go ahead and do my graph right here. So what does this graph look like? Well, it's h at t equals 0, and then it's just a downward half parabola, like that. And then you could get the time it takes to strike the ground, t here, I'm not going to give it another name, but the time it takes to strike the ground, t, well, I'll write t sub strike the ground, and strikes the ground, x equals h, and we solve for t, we find 2h over g, and then we have to take the square root. Okay. Here's another example where you have to go ahead and do this, okay? So I just wrote it down for you. Experience shows that just because you saw somebody do something doesn't mean you understood it. So you have to go ahead and, however many steps it takes you to do this, is to get from here, when it hits the ground, I'll put the subscript there, P sub s. When it strikes the ground, that much time has elapsed. And again, you can now plug numbers in, depending on if you know what the height is. Okay. So another interesting question is, we release an object from x0 sub h. Another question is, how far does something fall in t equals 1 second? Okay. So you release it from rest, how far does something fall in time equals 1 second? Then we're just going to imagine that the down is the positive direction. We can say the distance fallen is just 1/2 gt squared. Okay. We could either do it in this formula and solve for h, which is essentially what we're going to actually, since I'm using h, 1/2 gt squared. Again, this is something you want to figure out. Coming from here, well, when it hit the ground, x was equal to 0, and then I could solve for h and plug in t equals 1 second. Well, this is one of those cases where plugging in a number is important, okay? Because we know what 1 second is, 1001. That's a second. So let's go ahead and plug that in. 1/2 9.8 meters per second squared, 1 second the quantity squared. So being able to plug numbers in correctly is important as well. And you know, I'm even going to illustrate this one a little different. 1 second the quantity squared. I want to make sure we see the seconds in the numerator cancel against the seconds in the denominator. And they're squared here, squared here. So we're going to end up with meters. And now we can do 9.8 divided by 2, 4.9 meters. Okay, this is an important number. How much is 4.9 meters? I'm standing behind the table here. There's 1 meter. Here, let's do it at the board. 1. There's a second meter. There's a third meter. So the board is 3 meters up to the top of the ruler there. You need 2 more. 4.9, okay, just under 5. And we can't see the ceiling, but our ceiling is only about 4 meters here. So it's over 4 meters, and the question is, do you want to jump from there and land, say, on asphalt? Possibly not. Okay, you might get hurt. So something, if you drop something and it takes a second to hit the ground, say it's dark, then you'd probably know you don't want to jump. Okay, so yeah, that's an important quantity. 4.9 meters, 5 meters, 15 feet, 16 feet, if you're talking about feet. And that's how far something falls in 1 second when you release it from rest. Okay, so those are some important facts about free fall, and you want to be able to do all of these things. And then you can say, how long did it take to strike? Well, I don't have a calculator with me, but if you had 4.9 meters, you'd see, you'd get that 1 second back out just the way we plugged it in there. Okay. And in general, how long it takes to strike would be if you plug in whatever height you're at. Okay, so that's for free fall. Check the time once again. Excellent. Same thing now, vertical throw, but not from the ground. So once again, vertical throw. This is the original one I drew. Okay, so T, X, X0 finally strikes ground sometime here. So here's the point I want to make. If we have this formula and we want to find the air time, find T air, which is when it struck here. Okay, you want to find the air time. So we launched from an elevation and then it landed on the ground. Well, then you're going to take this formula, plug in 0, and you have to solve a quadratic formula. Solve the quadratic formula. Okay, that's no fun. I usually don't do that on in-class exams because we don't have time, and I probably won't do it for our online quizzes but yeah. It's not so great in an exam setting, but it's something you definitely have to know about. So you have to solve the quadratic formula, and ax squared plus bx plus c equals 0. Here's the general formula. Negative b plus minus square root of b squared minus 4ac. Okay, so that's if you actually have to solve a quadratic formula. But it's interesting. There are 2 solutions. 2 solutions here. Which one gives us the air time? Okay. So you're scratching your head about that. There are 2 solutions to this quadratic formula here. There are 2 times. And what you'll see is there's a plus minus, and this one would be the one with the plus sign. And what's the meaning of the other solution? What's the meaning of the minus sign? It's actually on this parabola here. Okay, so we launched here at t equals 0, so there's a minus t. There's a negative time at which we could have launched at the ground and had the same parabola. Okay. So solve quadratic formula, choose the correct sign. That's a judgment call on your part. What's the correct sign in the quadratic formula? Good, so that's a vertical throw as well. What that could be is I'm standing on a building and I throw something up in the air, it comes down and it keeps falling down to the bottom of the building, down to the ground below. So that would be an example for that. Okay, so let's say that that's enough for the free fall. Any question on free fall whatsoever, you can write these 3 formulas down and then start finding out what you know and what you don't know and work your way to the answer. So now I'm going to do a few problems just with constant acceleration using these formulas right here, okay? So free fall is a case of constant acceleration that's physically very interesting, and but constant acceleration problems can be interesting as well from automobiles, driving, and what have you. So that's what we'll do next. And I'll assign a combination of these 2 types of problems for the next homework. Okay, so just some more constant acceleration kinematics. So we need a good scenario. And I have a good scenario here. So imagine you're at the traffic stop, the light is red. And as soon as the light turns green, you're just going to accelerate forward with your car, okay? And let's say it's a constant acceleration. Okay, to make it a little more interesting, as soon as the light turns green, you notice that a bicyclist just came right next to you. So he blew right by you, even though you're in your car, right? Because you started from rest and he just came blowing by, timed the green light just right. So he's starting with you at the same time, but you're starting at 0 speed and he's starting with a constant velocity. Okay? So let's call this car and bicyclist. Okay, how about we'll call this car versus bicycle. Just a fair race at the green light. Now I'm going to graph it first, okay? Because it turns out that the formulas we need are all right here, okay? So we have x sub car versus x sub bicycle, x sub c versus x sub b. I'll call this x of t and this is t, and I'm going to graph them both in the same graph, which is kind of interesting. So what is the car doing? X sub car is starting out at 0 and it's starting from rest. So its graph is just a half at squared. 1/2 at squared. And x sub bicycle is starting out at the origin at 0, but it has a v sub 0 t and it has no acceleration. The bicycle's just cruising. So x sub bicycle is just v sub 0 t. We could call it v sub b if we wanted to. So if we graph both of these, we'll see the car is a parabola. Car is a parabola, half at squared. The bike is a straight line. Bicycle's a straight line. So this is x sub c and this is x sub b. So the question is, what is the significance of the crossing right here? Does this mean the car and the bike collide? No. They're side by side, but this time that corresponds to the lines intersecting is t sub pass, I'll call it. It's when the car passes the bicycle. The bicycle, got a jump on him, so to speak. The car is accelerating, so it's going to end up going much faster and pass him up. Okay. There's a constant acceleration example. Finally, so I'll make this my last example, and then I'll look up some homeworks for you. Finally, once again, this formula here, if we don't have any time involved, if no time is involved in the problem, we use v squared v0 squared plus 2a x minus x0, just as I did for the height. However, any problem that you can solve with this equation, you can solve using these two, right? Just 2 steps instead of 1. Okay, so now let's go ahead and consult the book for homework. And I'll just number this homework with the number of the lecture. So since this is lecture number 5, then this will just be homework 5 as well. Yeah. So let's see what we got here. So these will be in chapter 2. I have some ideas, yes. So chapter 2 or topic 2, but I just call it chapter because that's a habit. So chapter 2, this first one that I'm going to assign is the vertical throw. Okay, all kinds of questions about it. They even give you a number. So problem, it's always problems, okay? So it's problem 45. And what else do we have here? I have 3 problems, 50, 51, and 54. A couple of, they're all actually almost the same problem. There's nothing wrong with that, by the way. Slightly different formulations. The one with the helicopter is a little interesting because this one, the one with the helicopter, by the way, that is number 50. So number 50, you have to definitely use the full set of both of these formulas. And they tell us that the helicopter is descending, so you have to plug in a negative value for v sub 0, because it's like throwing something down. Okay, anything else? Yeah, excellent problem. I do want to mix one more into here. Ah, yes, and this 57 here, 57. So 57 is firing a bullet through a board. Bullet through a board. You're going to want to focus on this formula right here for problem 57. Okay, this is a good set of problems. These are, of course, next week. Okay, next week, so you can start work these over the weekend. Okay, that's good. See you guys next time.